guys, this is Professor Janacek, and I want to go over some examples of finding the derivatives of inverse trigonometric functions. Here at the top of the page, I have the rules for these inverse trigonometric functions written down. Let's go ahead and take a look here at example 1. We're going to take the derivative of the inverse sine of x squared minus 1. Well, according to the rules, the derivative for the inverse sine is 1 over the square root of 1 minus the argument squared. Well, our argument is x squared minus 1. Now, of course, the chain rule says we have to multiply by the derivative of that inside bit, that argument. Well, the derivative of x squared minus 1 is 2x. We can clean this up just a little bit. In the numerator, we have the 2x. In the denominator, we have the square root of 1 minus. Now, if we take x squared minus 1 and square it, that gives us x to the fourth minus 2x squared plus 1. Distribute that negative, combine some like terms. I think we end up with 2x over the square root of, let's see, it's a positive 2x squared minus x to the fourth. Now, yes, you could rationalize that denominator, but I'll go ahead and leave it there for now and move on to example 2, where we have d dx of the cosine of the inverse sine of x. All right, so in this case, I have a composition, so that definitely means we're going to need to use the chain rule again. The outside function is the cosine function. Well, the derivative of that is negative sine. Keep the inside function as is initially, and now we're going to multiply by the derivative of the inside. Well, that inside function, inverse sine, the derivative is 1 over the square root of 1 minus x squared. Now we can simplify this just a little bit. Here we're taking the sine of the inverse sine of x. That simplifies simply to an x. Of course, it's got the negative on the outside. We'll put that here in the numerator. The denominator is still the square root of 1 minus x squared. Again, you could go ahead and rationalize the denominator if you'd like. Example 3, we'll let f of x equal to x times the inverse tangent of x over 2, and we want to find f prime of 2 square root of 3. Now, be careful with this. Make sure you determine what f prime is before evaluating it. If you were to try to evaluate the function first and then take its derivative, things could go terribly wrong. So let's start by finding f prime. Well, we have x times the inverse tangent of x over 2. That looks like a product, which calls for the product rule. According to the product rule, we'll take the derivative of the first, which is 1, times the second, plus the first, which is x, times the derivative of the second. So here we have the derivative of the inverse tangent, which is 1 over 1 plus the argument squared. In this case, our argument is x over 2, so that gets squared. Now, the chain rule on this says that we have to now multiply by the derivative of that inside. Notice that argument x over 2 is what's inside. The derivative of that is 1/2. Now, it looks like we can clean this up just a bit. We have the inverse tangent of x for our first term. For the second term, let's see, that gives us x over, if I distribute that, well, if I have that 2, that's 2 times, oh, let me go ahead and move this over a bit. X in the numerator, 2 times 1 plus x squared over 4, if we square that, which we can distribute. So we have x over 2 plus x squared over 2. Now we don't want that complex fraction, so let's go ahead and clear that. We end up with the inverse tangent of x plus 2x over 4 plus x squared. Just take your time with clearing that complex fraction. So there's f prime. Now all we have to do is evaluate this at 2 square root of 3. So let's see, that gives us the inverse tangent of 2 square roots of 3. Oh, you know what? And I think I left off, oh dear, all the way back here. and here, and here. Oops. That should have been x over 2 from the very get-go. I had x over 2 as that argument. Oof, make sure I get that in there correctly. X over 2 and x over 2. Okay, that's looking better. Now, where were we? Evaluating this at 2 square root of 3, that gives us 2 square root of 3 over 2 as the argument of inverse tangent, plus 2 times 2 square root of 3 over 4 plus 2 square root of 3 squared, which is the inverse tangent of just the square root of 3 plus 4 over the square root of 3 over 4 plus, what do we get there? 12. Well, let's see. The inverse tangent of square root of 3 is pi over 3 plus 4 square root of 3 over 4 plus 12. Combine the terms in the denominator, and then I think we can reduce that fraction. We end up with square root of 3 over 4. All right, well, there you go. Not so bad. Just make sure you take that derivative and then evaluate it. And of course, don't forget all those little details, like keeping that argument as is. All right. Let's see. Example 4 here, we want to find the equation of the line tangent to g of x equals to the inverse secant of 2x at the point 1 pi over 3. All right, well, we're looking for the equation of a tangent line. So for an equation of a line, the things that we'll need, we need a point and a slope. A point which we'll call x1, y1, and the slope, which of course is m. Now we're starting with g of x is equal to the inverse secant of 2x. Of course, we are looking for the equation of the tangent line. Well, we already have our point. So I'll actually give myself a little more room. We'll let x1, y1 be the point 1 pi over 3. All right, so the point is taken care of, but now for the slope, we're looking for the equation of the tangent line. And a tangent line, the slope is the derivative. So we'll simply start by taking the derivative. So to find g prime, the inverse secant of 2x is what we're going to take the derivative of. Don't forget, we will need to, of course, use the chain rule because inside for that argument we have 2x. So we end up with 1 over the absolute value of that argument, which is 2x, times the square root of the argument squared minus 1. And then, like I said, we'll go ahead and multiply by the derivative of that argument. This is the chain rule, which gives us a 2 out here. Now we can go ahead and reduce. I see I have a 2 there. That 2 is in the absolute value, but of course the absolute value of 2 is 2. I can reduce that with the 2 out here. And then we'll also go ahead and simplify that 2x squared in the denominator. So we end up with 1 over the absolute value of x times the square root of 4x squared minus 1. Now, of course, for our slope, we want to evaluate this at our point. So we want g prime of 1, that is our x value. So that is 1 over the absolute value of 1 times the square root of 4 times 1 squared minus 1, which gives us 1 over the square root of 3. And I will go ahead and rationalize that, and that gives us square root of 3 over 3. So that's what we're going to use for m. All right, and so now we just need to use our equation of a line. We're going to use, you could use y minus y1 is equal to m times x minus x1, or you could use y is equal to m times x minus x1 plus y1. We'll go ahead and use that second version. So we have y is equal to square root of 3 over 3 times x minus 1 plus pi over 3. If we distribute square root of 3x minus the square root of 3 over 3 plus pi over 3, and so we can write this all as one big fraction. This is what? X times the square root of 3 minus the square root of 3 plus pi. All of this is over 3. And there we go. Enjoy!